All right, AP Calculus, we're here to talk about U substitution. So we've already had discussions about taking basic antiderivatives. And if all of the functions in the world were nice basic antiderivatives, then everybody would be happy and life would be simple. But unfortunately, the functions of which we've taken antiderivatives of so far are not as complicated as the ones that we're always going to see. So we have to kind of work our way up to these more complicated functions. What do I mean by that? For example, right now we can find the antiderivative of 2x plus 3 dx. Okay, we know that that's going to become x squared, and this term will become 3x, so we'll have x squared plus 3x plus c, and where everything is good. Okay, what if it was 2x plus 3 to the 8th power? Okay, well now we don't have a rule for this, a basic antiderivative rule. We do have a basic rule for x to the 8th, but not 2x plus 3 to the 8th. So we're going to have to work around this. We have to come up with a way to find this antiderivative. All right, keeping that same idea going, we know what the antiderivative of e to the x is. All right, that's the easiest one of all. We know that e to the x antiderives to e to the x plus c. Piece of cake. What if it was 3e to the 3x? Okay, ultimately we're going to see that this one is not that bad to find the antiderivative of. But we can't use our basic antiderivative rule because our basic antiderivative rule says we need e to the x. And we don't have e to the x here. We have e to the 3x. So how do we work around this? Okay, same thing we have in a previous video, x squared plus 1 over 2x. We can work with this. What do? Well, we can split this up into two fractions, x squared over 2x plus 1 over 2x. We have two fractions, or two rational expressions rather, and that allows us to antiderive each one individually. That's something we can do. Well, what if it's the reciprocal? What if we have 2x over x squared plus 1? We cannot split this up. All right, we don't have a monomial in the denominator. We have the binomial in the denominator. We're not allowed to put x squared in the bottom of one expression and 1 in the denominator of the other. We can't do that mathematically. We can split it up if there's a monomial in the denominator. We cannot split it up if it's a binomial or any polynomial other than a monomial in the denominator. How do we handle this? Okay. Well, the answer to finding the antiderivative of all of these three functions and many more is something called U substitution. Okay, and it is connected to the chain rule. Okay, and if we think about the chain rule back when we did our derivatives, the chain rule, we had the derivative of the outer function with the inner function, with respect to the inner function, and then at the very end we took the derivative of the inner function and we multiplied the two together. All right, you heard me say it in class over and over again. It's the the derivative of e to the ugly is e to the ugly times the derivative of ugly. All right, the derivative of the cosine of ugly would be negative sine of ugly times the derivative of ugly. But whenever we did our chain rules, we always finished it with times the derivative of ugly. So in other words, we had a product. So that product is going to come into play in this idea of U substitution. Okay, what am I talking about? Well, we're going to look to change. In essence, we're going to pick the ugly thing. What is our ugly item? Well, in this case, it would be great if we had just a variable to the 8th power. In other words, x to the 8th power, or u to the 8th power, or q to the 8th power. It doesn't really matter what the variable is. We're going to use u. But ultimately, we're looking to change this into that. Okay, u to the 8th du. All right, because this is something that we can take the antiderivative of. U to the 9th over 9 plus c. Okay, so we're going to represent, we're going to say, hey, what if u was equal to 2x plus 8? All right, then we can sub the 2x plus 8 out, and we can sub the u in. Right, now there's more that goes into this, and I'm going to talk about that in future examples, but that's our general idea. Same thing right here. What if we were able to have this 3e to the 3x turn into just e to the u, du? All right, because we need our differential to match up with our variable. All right, now we need a du, no longer dx. And again, that's something I'm going to talk about in the next couple of videos. But what if we could turn this into that? Well, this is a nice, easy antiderivative. All right, that's leading us towards e to the u plus c. Okay, that is something we can do. Same thing right here. Let me change markers to blue. What if we could turn this into 1 over u du? 1 over u. Antiderivative of 1 over u is going to work a lot like the antiderivative of 1 over x. What's the antiderivative of 1 over x? Yeah, it's going to be the natural log of the absolute value of x. So this is an antiderivative that we can do as well, except it'll be the natural log of the antiderivative of u. The natural log of the absolute value of u plus c. Okay, so that's where we're going with all this. Again, you're going to see it more in the examples, but this is our idea of u substitution. We no longer have easy problems to work with. We have much more difficult problems to work with. How do we handle it? Through u substitution. The idea behind u substitution: take something that's a messy expression in terms of x and turn it into an easy expression in terms of u. That's the general idea. The following videos are going to help you see some practice and how we can get this done.